locations of all 40 of our sensors. Or we can skip that. But hopefully, this gives you a quick indication of how well we can perceive the world around us. And in short, this architecture gives us a 360-degree view with overlapping redundancy, both per and across sensor modalities. And it lets us see at least 150 meters in all directions, and even more in the forward and rear directions. So why do we need multiple kinds of sensors? It's an important question. Why don't we just use cameras, which are the most similar to human vision? After all, people drive with our eyes, and so why aren't cameras enough? Well, first of all, computer vision just hasn't caught up with human vision yet. Humans are still much, much better at figuring out what objects are and whether there's something there at all. Deep learning is kind of sort of catching up, but not really and not particularly quickly, as it turns out. Second of all, cameras, like eyes, do not do so well when the sun is shining directly into them. And so when we're driving, we can actually move our head around, and we can even hold our hand up to block the sun. But of course, our cameras don't have that particular skill. Here's an example where we're looking into the sun, and our cameras do decently well. We can make out some pedestrians on the corner, and on the right, we see the top-down sensor fusion view, where they're shown as pink circles. So we do okay with cameras, even looking into the sun, right? Well, what's harder to see is there are actually a couple more pedestrians on the other side of the street, and the glare from the sun is completely washing them out. So our vision algorithms are failing to detect these pedestrians. My guess is that you would too. Looking at the raw camera data, which we're showing zoomed in here, it's essentially impossible to tell that there are two people in that crop. Fortunately, when you look at the view from the AI's full sensor fusion, we do detect the pedestrians, but we're detecting them with LiDAR and not with cameras. Here's another example. Pedestrians at night have a lower signal-to-noise ratio and are more difficult to see. This is just basic physics. When there's not as much light, images are noisier and or blurrier, and you've noticed that on your smartphone cameras. Now, these days, they all have night mode, but that requires you to stand very still while they capture a long exposure. And so that doesn't really work while we're driving around. If a pedestrian's clothing is a similar color to the car behind it, especially at night, then the contrast is poor and it's difficult to distinguish the person. Furthermore, motion blur can also degrade image quality, leading to detection failures. In theory, we could just jack up the sensitivity to detect anything that might be a person or something else. But the challenge is that doing that would lead to a significant increase in what's called false positive detections. A false positive is when the AI imagines there is something that is not really there. This is uncomfortable at best and sometimes even dangerous because the vehicle will unnecessarily slow down, unexpectedly stop, or even try to swerve around non-existent obstacles. So in order to build an autonomous system that is truly safe, we must detect everything that is there, but also know when there is nothing. Okay, so we've talked about some of the limitations of cameras, but it's not fair to just pick on cameras. LiDAR gives us a fairly dense 3D view of the world around us, and it has the wonderful property that it measures exactly how far away everything is. But to be fair, it has its issues too. And not just that the richest person in the world thinks they're too expensive. Although, serious point, it's really not that expensive when you use them in a robotaxi business model. Anyway, here we see one of our L3 vehicles driving autonomously in the rain. And on the left, you can see the raw LiDAR output, as well as the obstacles that our LiDAR pipeline detects in real time. Unfortunately, LiDAR often returns a signal when it hits water droplets. And a naive perception algorithm would then try to stop for rain, which would be pretty dumb. One of the cool things our perception team has figured out how to do is use the LiDAR intensity values, dual return mode, and the organic shape of water blobs to automatically filter out moisture like rain, fog, and steam from the perception output. It works really well, but it's still important to have other sensor modalities to corroborate the final output. Speaking of steam, we have a secret weapon for that too. It turns out that long-wave infrared cameras, which sense heat, can see right through steam. Here's an example of that, and it's pretty cool. You can see the steam occluding the pedestrian in the camera view, and even LiDAR wouldn't be at its best here. But the long-wave AR camera sees the person as they pass behind the steam. So worst case, even if our cameras, radars, and LiDAR all miss something, our long-wave AR cameras will pick up living things since they emit heat. Fundamentally, we just want to understand characteristics of objects around us like depth, velocity, intensity, RGB color. And so this requires a mix of multiple sensors like cameras for color sensing, radars for velocity, long-wave radar for heat, and lidars for depth. It's the combination of all of these sensors that gives us an unparalleled and redundant coverage of the scene. The spider graph shows how we do really well overall, even though no one individual sensor is a panacea. In addition to making sure our overall sensor modalities work well together, it's important to address redundancy and independence of the sensor pods as well so that we can maximize overall safety. Because we want to make sure that we can see objects from every single corner. So our goal is essentially to overwhelm our perception system with data so that as we then go through prediction and finally motion control, we can feel confident in our understanding of our surroundings. Then we can use simulation to further test these various modalities and evaluate them against our safety case. Here you can see how we test individual modalities in simulation and understand how they work together. Working our way from the left, we see simulated radar, and then LiDAR, and then cameras, and then finally our full sensor fusion output all the way on the right. Simulation lets us test our entire sensor suite, as well as remove an individual sensor or modality of sensor to see how the vehicle would perform in a degraded state. A huge advantage here is that even if one of our sensor simulations isn't quite perfect, the overall 3D output is still representatively accurate in terms of performance and noise models. And this also lets us run our entire AI stack in simulation, not just perception. We can then create simulated scenarios to further test and validate how the vehicle will respond to edge cases, which are those rare but complicated situations that the vehicle must be able to safely navigate. And while real-world testing is crucial, the advantage of testing in simulation is that you can run an extremely large number of scenarios, including ones that would be too dangerous to do in the real world. And you can do that quickly, precisely, and most importantly, safely. So that's all great, but how do we know when we're finally safe enough? Prior to each internal milestone, we use a fault tree, kind of like the one shown here, but this is, of course, a bit simplified. Hope you don't mind, to predict the overall residual risk that the Zoox vehicle might introduce into a defined driving environment. Now, the overall predicted residual risk, including severity, is compared to human data, like crash, injury, and fatality rates, to determine whether or not we're ready for the milestone. In addition to building safety features throughout the process, we've even added a separate system that provides a truly independent layer of oversight and control. We call it Safety Net, and it uses a deep learning model on all of the sensors to predict occupancy and velocity in the future all around the vehicle. As you can tell, our software is a critical component to achieving autonomous driving, and vertical integration with hardware is the ultimate competitive advantage to finally achieving full autonomy. So autonomous vehicles offer a once-in-a-lifetime opportunity to transform mobility. When you're working on transporting people rather than goods, it's critical that your entire system is safe enough for people and not just pizzas. And our vehicle engineers have worked really, really hard to make sure that's true. So even if we build the best AI system in the world, which is exactly what we're doing, we still can't prevent 100% of collisions, because somebody could still run into us when we're just minding our own business. And even though that won't happen often, we do need to be prepared. So our approach represents a fundamental shift from reactive to proactive safety. We call it prevent and protect. What we mean by that is we're using technology to prevent every crash that we can, including the 94% that are caused by human errors. But we're also protecting riders with innovative safety features in case something unexpected happens. And if we drive enough miles, we will encounter other road users who do things they shouldn't. So we need to be as prepared as possible. We've designed advanced safety features into every element of Zoox, including an innovative airbag that inflates between riders and cushions your head, neck, and chest in a totally new way to keep everyone separated and protected. So that's our approach. How are we doing? Well, not only are we getting better and better at driving in dense urban environments with our L3 test vehicles, we've also made significant progress driving our own ground-up robo-taxis with nobody in them. We recently completed a critical checkpoint that we haven't talked about publicly yet, operating our vehicle with no one inside, no chase vehicle, and no emergency stop, all on open, private roads with non-Zoox agents, including pedestrians, cyclists, cars, and trucks. And then most importantly, validating all of that with our quantitative safety case. This means we can operate in an unstructured environment at human plus safety levels, and we're almost ready to do that on public roads. The opportunity to reimagine what the future of mobility can look like is immense. We are excited and privileged to get to work on something this worthy, and we can't wait for customers to be able to experience the magic that is riding in a Zoox. It's a categorically different experience than getting in the backseat of a car, whether or not there's someone up front driving. Please follow us along our journey, and I hope you can all experience Zoox in the next few years. Thanks so much.
Please welcome author, science TV correspondent, and radio host, Michio Kaku.
Well, after such a great introduction, I can't wait to hear the speaker myself. You know, I have the privilege of being able to interview on television some of the world's great scientists. And every time I interview these scientists, I ask them the key question, the most important question of all. The question I ask them, this great question, is there intelligent life on the Earth? Well, I was watching the Kardashians on TV last night. And sometimes you really wonder. But one thing for me is very certain, and that is that in this room, we have some of the great minds, the most energetic, the most inquisitive minds. You are the makers of the future. So applaud yourself for being some of the most intelligent people around. In today's talk, I'm going to talk about the exploration of outer space. I'm a physicist. We're going to go centuries, millennia into the future. And who knows, maybe we'll encounter intelligent beings as we venture into the galaxy. But you know, I get a lot of emails. And some of the emails say, "Professor, you're wrong. You are really wrong. The aliens are not there. The aliens are here." And then I say to them, "How do you know that the aliens walk among us?" And they say, "That's because they've been kidnapped. They've been kidnapped by flying saucers." Well, I say this: the next time you are kidnapped by a flying saucer, for God's sake, steal something. An alien chip, an alien paperclip, anything, because there's no law against stealing from an extraterrestrial civilization. No law whatsoever. And we need proof that there is something out there in the universe. Well, today, we're going to talk about the future. And I've had the privilege of writing 5 New York Times bestsellers about the future of robotics, the future of the mind, when we communicate telepathically through the internet. My latest book is called The God Equation, about what I do for a living. I work on something called string theory, which we think, but cannot yet prove, is the theory that eluded Einstein for the last 30 years of his life. A theory of everything that says that all the subatomic particles we see in nature are nothing but vibrations on a tiny vibrating string. So what is physics? Physics is the harmonies you can make on these tiny vibrating strings. What is chemistry? Chemistry are the melodies you can play when these strings interact with each other. What is the universe? The universe is a symphony of strings. And then what is the mind of God that Einstein labored for so many decades of his life? The mind of God would be cosmic music resonating through hyperspace. That would be a candidate for the mind of God. But today we're going to ask a different question, and that is life on the Earth. Did you know that of all the life forms that have existed on the Earth, 99.9% of all living creatures eventually go extinct? Let me repeat that again. 99.9%